Hi folks, we're going to take a look at page 208, number 11. So let's take a look at the question. It says a train leaves the station at 10 a.m. and travels due south at a speed of 60 kilometers an hour. Another train has been heading due west at 45 kilometers per hour and reaches the same station at 11. At what time were the two trains closest together? Okay, so this is one of these questions where I think drawing a good diagram is going to be imperative. So let's see what they tell us. They say that 10 a.m. a train leaves the station. So let that be the station, and it's traveling due south. Okay, so starts at 10, travels due south at 60 kilometers an hour. And at the same time, we have another train that's moving westward, okay, towards the station. Okay, and what we're looking for is the minimum distance between them. Okay, so what I'll do is I'll use this line here to represent the distance between them. Okay, and I'll use capital D just to not confuse it with the D we use for the derivative. Okay, so now we have to set up an equation for this expression here. Okay, now since we're looking for a distance, what I'm going to want to do is work with distances in my equation as opposed to, or even in my diagram, instead of velocities. Okay, and I hope you'll notice that we do have a right angle triangle that gets formed by the distance traveled by the first train and the remaining distance traveled by the second train. Okay, so this is what we're going to try to do. So let's start with train A. It's moving at 60 kilometers per hour. Okay, so what I'm going to do is I'm going to let t be the time elapsed, okay, from 10 o'clock. Okay, so we'll let t equals 0 represent 10 o'clock. So let t equals 0 be 10 a.m. Okay, so that means that this train, since it's going at 60 kilometers an hour, would have traveled 60 times t kilometers. Okay. Now, in that same time, okay, the second train would have traveled 45 t kilometers. Okay. Now, by the way, let's put a constraint on t here. So since this train leaves at 10 a.m. and that train will have arrived at the station by 11 a.m., this is all happening within 1 hour. So t here is going to be greater than or equal to 0. Okay, so this is going to happen after 10 a.m., but before or perhaps at 11 a.m., which is 1 hour later. Okay, so problem is that this distance here, okay, is 45t, but what I would really like is the remaining distance to the station so that I can use my right angle triangle and make use of Pythagoras. So we have to think how long this train is traveling for. So say this is its position at 10 a.m. It reaches the station 1 hour later at 11 a.m. Okay, since it's traveling at 45 kilometers per hour, in that 1 hour, it would have traveled 45 kilometers. Okay, that means that the remaining distance, okay, this length here, can be represented by 45 minus 45t. Okay, so the total distance of 45 kilometers minus the distance it actually traveled during that time t. And now I have enough information to create my equation. Okay, so the distance, okay, is just going to be the hypotenuse of this triangle. So it's going to be the square root of 60t squared plus the square of the other leg. So 45 minus 45t all squared. Okay, and now I've got a function given with respect to one variable. I have the constraint on my variable. Okay, so I've created my model. So now we'll do part 2, which is going to be the calculus. So let's figure out the minimum distance. Now this is a closed interval, so we know that we're guaranteed a minimum distance. So it's either going to occur at 0 or 1, or possibly at a critical point if there are any. Okay, so I think the best thing we should do is simplify this here first. Okay, so here we've got 60t squared, so this is 3600t squared, plus we have to square this binomial. So let's just take a quick look here, 45 squared. Okay, if you can see that, 20.25 or 2025. So 2025. Then we have to do twice the product of first and last. Okay, so 45 times 45 is 2025 times 2 is going to be, I guess it's going to be 4050 t plus 45t all squared. So that's going to be 2025 t squared. Okay, and let's bring all the like terms together. Okay, so here we've got 3600, 4600, 5600, 5625. So 5625 t squared minus 4050 t and plus 2025. Okay, so there's my simplified distance equation. So now let's take the derivative. Okay, so it's 1/2 times this whole expression, 5625 t squared minus 4050 t plus 2025 to the negative 1/2 times the derivative of that. So that's going to be 2 times 5625. Let me just check that here. 5625 times 2. So 11250. So this is going to be 11250 t minus 4050. Okay. Now, I might skip the next step, but I'm going to write it out just to indicate exactly why this is working. So first of all, I want to determine when the derivative is 0. So here, the only thing left in the numerator is the 11250t minus 4050. Okay, and in the denominator, I've got 2 times the square root of 5625 t squared plus 4050t plus 2025. Okay, but this works out nicely because I've already got this as one fraction. So in order for this fraction to be 0, I just need the numerator to be equal to 0. Sorry about that. So that means t is going to have to be equal to 4050 divided by 11250. Okay, so there's our critical point. So here we've got, what was it again? 4050 divided by 11250. Okay, which gives me t at 0.36. Okay, so first of all, I do notice that this does fall within the range of my t values, so I am going to consider this critical point. Okay, now the question is it going to be a max or min? Well, let's look at d prime here. So let's look at this expression for d prime. Okay, we notice that the denominator is always positive, so I only have to look at the numerator. Okay, so it's 0.36. Okay, and notice this is just a linear function with a positive slope. So I know that that has to cross the x-axis and go from negative to positive. Okay, so you see with this little trick, I was able to avoid having to stick t values into this equation here. Okay, so only interested in the numerator. It's a linear function with a positive slope, so it has to go from negative to positive at the 0. So we do indeed have a min. Okay, so now we just have to determine what the maximum and minimum are. Okay, actually all we care about is the minimum distance. So if we take d at 0, which is one endpoint, stick that into there, and we've got, this just goes to 0, 45 minus 0, so we've got the square root of 45 squared. Okay, so that's just going to be 45. Oh, there we go. If we take d at 1, which is the other endpoint, okay, let's go to our equation here. So here we've got 60 squared plus, this is just going to be 45 minus 45, so that's going to be 0. So square root of 60 squared is just 60. And now if we take d at 0.36, okay, let's calculate that here. So we've got the 60 times 0.36. Okay, and square that. Okay, plus, let's put this whole thing in brackets. 45 minus 45 times 0.36 squared. Okay, and I have to take the square root of that, so we'll do exponent 0.5, and here we have 36. Okay, and so we see that at the critical point is where we have the minimum distance. Okay, now this is the answer based on our algebra. Now let's actually go back to the question and see what they're actually looking for. So it says at what time were the two trains closest together. Okay, so we haven't actually answered the question here. So it takes 0.36 hours. So it's going to be 10 o'clock plus 0.36 hours. So let's figure out what 0.36 hours is. So 0.36 times 60 minutes in an hour. So here we've got 0.36 times 60, so 21.6. Okay, so that means that the time that this occurs is at 10:21.6 okay, a.m. Okay, so that's it. So just a reminder about what we did. We set up our diagram, determined our constraint to find our model. Then we did the calculus. Okay, determined that the minimum value occurred at the critical point, and then we answered the question that was actually posed. So I'm just going to back up here and try to give you a sense of the whole solution. Okay. And I'll have to figure out how to get the lighting. There we go. Maybe let's get the light out of the way. Okay, and that is it.